Hi everyone. So till now we have looked at what a linear regression is and how we can think about linear regression intuitively. But now let's look at some of the implicit assumptions that we made along the way. We have stated some of those when we were deriving the proof for this, but let's kind of pinpoint what are the assumptions for a perfect linear regression and what happens if we break those assumptions. So starting off, the first assumption is the assumption of linearity. Now, this is the very basic assumption. We also started with an example where we had advertising expenditure, which was a direct proportion of daily sales, and we were able to draw this line out. But what happens if I keep increasing the advertising expenditure above $1,000, let's say up to $4,000? What happens is I can see that my sales is starting to stagnate at a certain level of advertising expenditure, and this relationship between advertising expenditure and sales revenue is not linear anymore. Now, this is crucial. This is what happens in real life. We don't always have linear data sets, and we don't always have data sets that keep following this linearity relationship. And often in real life situations, what we do is we see what is the range of real life data where this linearity holds. And we'll make predictions of the dependent variable, in this case sales, only in that region where we know that the linearity holds to be true. Now, another example that I want to mention here is, let's say, study time versus exam scores. Let's say there's a student who studies for X number of hours, and this is the score for those students depending on how much they studied for the exam. Now, intuitively, it makes sense that the harder you study, the better your exam score would be. But how do we measure the hardness of how hard someone worked, right? We can only measure how long they worked, which is somewhat an approximation of how well you understood the concepts and so on and so forth. But not necessarily. If you keep studying for longer and longer hours in one single day, you might actually saturate. And the other thing is, after a certain number of hours, your increase in score might just be very less compared to the amount of hours you put in, right? So this again is an example of non-linearity, where linearity might hold for a certain set or a certain range of values of the dependent variable, where you can predict with certain confidence that the exam score is going to be this, right? And this is very real. In real life, you will always have data which only satisfied linearity in a specific range or under specific conditions. And it's important, if you're doing real life statistics, to know what those conditions are. Moving on to the second assumption we made but have not talked about. This is the independence assumption. Now, what do I mean by independence assumption? Let's take another example. We have time series data of daily stock price, and let's say the stock price is varying as per the day, and this is the price of the stock on day, let's say 21, on day 22 it's this much, and so on. Now, if you were to fit a linear regression into this model, let's say if I were to fit it up to day 60 from day 10, I can see that this somewhat follows a linear relationship, where maybe I can probably fit a line like this, right? Now, this is a pretty good fit for the data that we have, right? But this does not mean that you can predict the next value directly because your fit is good. In this case, each stock value is dependent on the last day's value as well, right? The stock values, which is the y values on each successive x, are not independent. So what independent assumption says is your data set and the values that you are recording, x comma y, they should be independent of each other. So each value in the data set should be independently recorded and should not be dependent on other values of the data set. This condition breaks down in the case of my time series data, where I am measuring daily stock prices. Now, you might think that my linear regression is a good fit for the data, but it may not predict the next value very well, because the linear regression will say, okay, you can go like this, but the next values are something very different. Again, they depend on macroeconomic factors, the stocks, intrinsic financial factors, and so on. But leaving those things aside, the basic mathematical concept which is at play here is that these values are correlated and are not very independent to each other. And that's why a linear regression might not be the best fit, right? So what are we essentially trying to do with these assumptions? We are trying to test the perfectness, in some sense, of this simple model that we defined, y is equal to beta 0 plus beta 1x. We are trying to see in what cases this model makes sense and in what cases this model can be broken down, or this model can give us results which may not align with reality. And those conditions we are trying to list down. The first one was linearity. This is independence. Both real world examples, and both are very crucial when you are thinking about finding the best model to model your data set. Now, the third assumption that we made was homoscedasticity. Now, this is a very complex looking term, but it's not very complex, to be honest. Homoscedasticity means that your deviation of residuals around your line, around your best fit line, should be uniform and should not have a skewness in one direction or the other. What do I mean by that? So for example, let's say I fit in a simple line here, right? This is the line that I am fitting, and this is the best fit line. Assume that. You can see that the scatter of all these points around the best fit line in the initial values of x is less compared to the later values of x. Now, this is not homogeneous, right? This is a classic example of heteroscedasticity, where you have the scatter of the best fit line is changing, where these points are more far away compared to the points at the initial values of x. And this is a problem. Why is this a problem? Let's think. Let's say you have this best fit line, and now as you try to predict something, predict a value of y based on x. Let's say you try to predict for this particular x value, the variation here would be very high compared to a prediction you would want to make at this point, right? And that's a limitation of the model. Even though the model gave me this line, I cannot confidently predict the value of y for a higher x, and that's a problem because my model is skewed into one direction. So continuing from the previous assumption that we had, that the graph should be homoscedastic. Now in this case, it's not. My scatter is different, and my scatter is more in this direction or even this direction. My scatter is more at higher values of x compared to lower values of x, right? Now, another thing that we need to check and we should make sure is the residual amount. So the residual is predicted y minus the actual y, or vice versa, and then we plot a frequency distribution of the residuals. And this, in this particular case, my residuals are more skewed towards negative side, because my graph, which has a 0 at this point, has a negative skewness. So residuals are negatively skewed. What does that mean? Let's say if I take this one. So let's say I draw my best fit line again here. And now what do I mean by this residual being skewed in one direction? Is that my residuals are more scattered in this direction compared to this direction. So this is flatter compared to this. Now it may not be evident at first go if you're looking at the graph, but it's always best to draw a normal distribution of the residuals to see if there's any unnecessary skew in one direction compared to the other. But then you might ask, why is my line like this? If there is more weight in this direction, if this end is fatter compared to this end, shouldn't the line get skewed automatically when we are doing sum of squares, right? When we are trying to minimize the error, shouldn't the line go down a bit? And that's a very good question, which brings us to the next part, which is outliers. And outliers are these extreme values, which, let's say in this case, I have an outlier around 16, which is a very high value compared to the rest of the data. And this one single point being a higher value compared to all the other data is trying to pull this line back up, right? Even though this data is trying to skew and push the line towards bottom, this few outlier, or in this case this one outlier, is trying to pull the line back up. And that's why your minimized error line looks somewhere like this, and it has both a skewness. So this line has skewness in the negative direction, and that is balanced to some extent by outliers in the positive direction, right? And all of these things are detrimental to a perfect linear regression because they are somehow skewing your data, which is making your future predictions more unpredictable, right? So again, coming back to the core idea, what we are trying to do, we are trying to make sure that a linear regression is a perfect model for prediction of future values. And we are evaluating case by case all the assumptions or all the places of why those predictions can go wrong. So in future, when you're designing a model or thinking about model design, which model to use, you can think about these cases as reasons of why your real data does not correspond to what you predicted. So I hope this makes sense. Normality, we did an assumption of normality. We also looked at homoscedasticity. So homoscedasticity and normality are very closely linked because you are actually seeing how residuals behave and if there is skewness and outliers in the residuals themselves. Now, another method to check normality is QQ plot. So let's look into what QQ plots are. Now, QQ plots are quantile plots. I know the names can be slightly tricky. The names can be slightly tough, but the core concept that underlies QQ plots is very, very easy. So to understand QQ plots, we need to understand what are quartiles and quantiles. Again, very easy concepts. Once you understand what they actually mean, it will become very intuitive to grasp why this is a good method to check normality. So what is a quartile and what is a quantile? Let's take this probability distribution. We have this probability distribution in which I added 3 lines to divide this normal distribution into equal parts. So 25% of all the data lies in this one, 25% of all the data lies between Q1 and Q2, 25% of all the data lies between Q2 and Q3, and the rest lies above Q3. So you need 3 lines or 3 markers to divide a single data set into 4, right? And that's what quartiles do. Quartiles essentially divide my whole data set into 4 equal buckets. That's it. And quantiles, on the other hand, can divide my data set into n different buckets. Now I can define n to be 4. If n is 4, my quantiles are my quartiles. If n is 100, we call these percentiles. So let's say any number of equal parts you divide your data set into, and that becomes your quantiles. So in this case, if I divide it into 100 small parts, so let's say if I have a data set and I introduce 99 markers in between those data sets, I have 100 equal parts, and those 100 equal parts, that division is called quantiles. So this is the first quantile, this is the second quantile, and because this is 100, I can say this is percentile. So first percentile, second percentile, third percentile, up to 100th percentile. Now, one more illustration that I want to do here, which is very important, is you might think intuitively, let's say if I have a normal distribution, you might think that, okay, this division lies at equal intervals. That only happens if you have a uniform density. So if you have uniform number of readings spread out, then that's when you'll have equipartition. But this equipartition will not be happening in a normal distribution, because what you have in a normal distribution is very less values on each extreme, right? And the values keep increasing towards the mean. So one percentile, the X range of one percentile can be huge compared to if you go from 25th to 26th percentile, right? This X range can be very less because you have so many values that are between 25 and 26th percentile, or you have the most values around 0, which is around the 50th percentile, right? So don't let percentile give you the impression that even though you are dividing the data set into equal number of values in each percentile, that may represent different areas or different range on the independent variable. So that's something that I want to mention as a caveat, because sometimes people assume that, okay, if I'm dividing my data set into 100 equal parts, that means each part will have equal domain or equal range of the dependent variable into it. That doesn't have to be. So coming back to what a QQ plot really is. So on one side, let's say we have this uniform normal distribution, and let me just erase this part. What I have here is, suppose we draw percentiles. So I have something like the first percentile somewhere here, the second percentile, the third percentile, and so on up to the 100th percentile, right? So I've distributed my data set or the data into 100 equal percentiles, and I draw these markers. So suppose the first percentile lies at somewhere around -2.7. I'm just marking it out for convenience. And let's say we take this data. Once we have these residues and we have plotted them as a frequency distribution, I can also draw quantiles in this one. So let's draw percentiles here. So let's say your first percentile happens to be somewhere around 19 or 20,000, negative of 20,000, and the second percentile somewhere negative 18, 17,000 or something, and so on and so forth. You draw all the 100 percentiles here. Now what I do is I have my data quantiles, which is this one on the y-axis, and the normal distribution quantiles on the x-axis. I will draw my first percentile here on -2.7 or something, right? So this is around that number. I'll draw my uniform normal percentile here. And then what I'll have is I'll also draw my first percentile from my sample data, which is around negative of 20,000. And I'll draw it parallel to the x-axis, right? So y markers are actually my sample percentiles, and x markers are actually my theoretical or a uniform normal percentile. Once I draw those, the point where it intersects, I'll mark that down. And I'll keep doing that for each and every percentile. So I'll have 100 points marked down. And now, suppose what would happen if I had everything as perfect. What do I mean by perfect? If my sample quantiles or sample percentiles followed a perfect normal distribution, these two, the quantiles that I draw from these two graphs should fall on a straight line, right? If they don't fall on a straight line, that means my sample data is not a representative of uniform normal distribution. And that's it. That's the whole concept of QQ plots. It's a visual aid in which we can quickly check if my residues are following normal distribution or not. If not, how far away are some of my quantiles, or how ill distributed it is compared to a uniform normal distribution. So I hope that makes sense. And the last and the final assumption that we did in all of this, and I want you to guess what this multicollinearity means. So again, heavy terms, very simple meaning. Go back to the derivation we did in the start. We derived these beta 0 and beta 1 by following a simple assumption that partial derivative of beta 1 with respect to beta 0 is 0, and partial derivative of beta 0 with respect to beta 1 is 0. What does it mean? Intuitively, it means that both of these variables, both of these parameters of the model are truly independent and are not correlated with one another. In real life, the correlation can exist, and that can become a problem. Let's look at it from an example. So let's say you are trying to predict the value of a house based on size of the house and number of rooms in the house, right? So if you're trying to do this and you assume, let's say, a linear relation, value of a house is equal to beta 0 plus beta 1 times size plus beta 2 times number of rooms. One thing that we did wrong, although mathematically we haven't yet started anything, right? One thing that we intuitively did wrong was to assume this formula where beta 0 plus beta 1 times size plus beta 2 times rooms, because number of rooms is highly correlated to the size of house. If you're getting a bigger house, almost always it means that you'll have more rooms compared to a smaller house, right? And if I were to plot number of rooms with the square footage of size, it is very, very highly correlated. It's almost a linear relationship, right? So what can I do? I can represent size as a factor of number of rooms, right? If I can just say number of rooms is equals to some constant, which is, let's assume beta 3 in this case, times the size, right? And some other constant, beta 0, okay? I started off by this equation. Assume that the number of rooms is very highly correlated with your size of the house. Then you can essentially replace one variable. You can get rid of either the number of rooms or the size. You can represent number of rooms as some constant times size. So essentially you will again end up with one equation. So in this case, you can reduce the dimension or the number of independent variables because one variable is not truly independent. And this is a perfect case. This is a case where we assumed that there are two independent variables who follow a perfect linear relationship. But you get the idea, right? If we have dependence or if we have correlation between the independent variables, it is going to mess with the prediction. So this was a very simple case where we expressed the independent variables as related linearly, and then we are able to plug this in back to the equation to get a single dimension equation. But there can be cases where you can't do that so simply. So in those cases, what we do is something called as principal component analysis. Principal component analysis is a fancy term where you do exactly the same thing that we did here. But again, this was a very simplistic case. We were able to do it very easily. But when you can't do it, when the relationship is not very obvious, we generalize it and we try to bring down the dimensionality, and we try to only use the variables, or we try to modify them in such a way that we use modified variables, which are less number of variables, so that those principal variables or those limited set of variables define the most about or are the best predictors of the dependent variable. So what it essentially does is we take all these number of variables which may not be independent in the true sense, and then we reduce the dimensions or reduce the independent variables, and we have transformed these variables and use these transformed variables to actually make the prediction, because they represent almost all the variation or all the effect that you need to capture of about the model, right? And that's what PCA actually does for more complex cases, but the intuition remains the same. So essentially, if multicollinearity did not hold, we would not be able to derive the basic values of beta 0 and beta 1 that we started off with, because our first assumption would not hold true.